Welcome to this explainer. Today, we're going to demystify exactly what happens under the hood when you run a Python script. If you're coming from a compiled language background, you probably have some preconceived notions about how Python operates. Well, we're going to explore this together, and by the end, we're going to build a clear, super easy to remember mental diagram of the entire execution pipeline. You'll know exactly where your code lives, how it runs, and where the performance bottlenecks really are. Let's get into it. Here's our roadmap for today. We're going to bust a major myth about interpretation, map out that execution pipeline diagram, peek inside the virtual machine, tackle memory and the GL, and finally see how modern AI completely escapes Python's limits. Okay, Section 1, Unmasking the Python Myth. Let's start right at the foundation and address the elephant in the room. So is Python really interpreted? Most engineers transitioning from C or C++ just assume Python is interpreted line by line, kind of like a simple bash shell script. You type a line, it runs immediately, right? Well, looking at the source material, I was actually surprised to learn that this is not the whole truth, not even close. The crucial takeaway here is that Python actually belongs in the same family as Java. It doesn't just read and react. CPython compiles your source code ahead of time. Yes, you heard that right. Python literally compiles your code. And this really illustrates the massive difference between the two paradigms. When you compile C++, it goes straight down to native machine instructions tied to your exact CPU hardware. But Python, it compiles to a portable set of instructions called bytecode. This bytecode isn't meant for your physical CPU at all. It's understood only by CPython's own software-based C interpreter. That is an absolutely crucial distinction to anchor in your mind. Moving on to Section 2, the execution pipeline diagram. Let's see how this all builds into that easy-to-remember visual. Okay, I want you to picture a factory assembly line in your head. This is our mental diagram, and it has 3 distinct steps. Step 1, your source text is broken down into tokens. And because Python cares so much about indentation instead of curly braces, the tokenizer specifically tracks whitespace. Step 2, those tokens are fed into a peg parser to build an abstract syntax tree, or AST, representing the logic. And finally, step 3, the compiler walks that tree and turns it into bytecode. Now, what's really fascinating here is where that bytecode actually goes. It gets packaged into something called a code object. Every single function, module, class body, or even a tiny lambda gets its very own independent code object. This isn't just plain text, it's a real heap-allocated object holding the raw bytecode bytes, your constants, and your variable names. It's a fully compiled block of Python just waiting for action. And to save time on this assembly line, CPython caches these code objects straight to your hard drive as .pyc files inside that familiar _pycache folder. This happens whenever you import a module, which lets Python completely skip the compiling step on future runs. It is basically the closest thing Python has to an incremental build. But a quick side note here. If you run a script directly from the command line, it compiles fresh into memory every single time. Nothing is saved to disk for your main script. Section 3, Inside the Virtual Machine. Now that we have our bytecode securely wrapped up, we hand it off to the PVM. Let's compare the engines for a second. A hardware CPU running C++ uses a register machine, juggling values in lightning-fast hardware slots. The Python virtual machine, however, is a software-based stack machine. It pushes and pops values onto a stack. Think of it sort of like a stack of plates at a buffet. It intentionally trades having fewer overall instructions for incredible simplicity, mainly because it doesn't have to worry about allocating hardware registers. So how in the world does a stack machine handle function calls? Well, it uses frame objects. A frame object is the PVM's version of a call stack entry. But remember, because we're in Python, this isn't just some lightweight pointer moving up and down a native C stack. It is a fully fledged, heap-allocated object containing a value stack, local variable slots, and a link back to whoever called it. Because the PVM allocates real, heavy memory objects for every single function call, deep recursion requires serious overhead. This physical reality is exactly why deep Python recursion is so much slower than C++, and it's exactly why the sys.setRecursionLimit command exists. It's literally a safety valve to protect your interpreter from a total memory crash. But hey, the PVM is getting much, much smarter. While it doesn't generate native machine code by default, it's undergoing a pretty rapid evolution. Back in Python 3.11, it introduced in-place specialization, meaning it rewrites hot bytecode on the fly when it sees the same data types over and over. Python 3.13 brought us an experimental just-in-time or JIT compiler, and moving into 3.14 and beyond, we're seeing major JIT improvements. Python's engine is constantly adapting to run your bytecode faster. All right, section 4, objects, memory, and the GL. To truly grasp Python's performance profile, we have to look at how it manages state. Consider a simple integer. A C++ integer is typically just 4 raw bytes sitting in line in memory. No headers, zero overhead. A Python integer, on the other hand, is a full heap-allocated struct. It carries a type pointer, a reference count, and the actual numeric payload. This means a simple arithmetic loop is naturally going to be slower in Python purely because every single number requires dynamic type checking and object overhead. CPython manages all these heap objects in 2 distinct steps. Step 1 is reference counting. Every object tracks exactly how many things point to it. When that count hits 0, boom, it drops immediately. It's conceptually similar to a C++ shared pointer. Step 2 is the generational garbage collector. This runs periodically to detect and break reference cycles. You know, like when 2 objects point only at each other, creating a little isolated island stuck in memory forever. But there's a massive catch with reference counting. It's not thread safe by default. If 2 threads try to update an object's reference count at the exact same time, it corrupts the memory. So CPython relies on the infamous global interpreter lock, or the GIL. The GIL is a single global mutex, ensuring only one OS thread executes Python bytecode at any given moment. And this is the painful reality. 10 threads doing pure Python math won't execute 1 bit faster than a single thread because they're all just waiting in line for the lock. However, the landscape is shifting right now. We are experiencing a monumental shift because the GIL is actively being phased out. Starting in Python 3.14, there is an official opt-in free-threaded build that completely rips out the GIL, replacing it with finer-grained internal locking and biased reference counting. We're looking at a multi-year migration where the GIL will eventually be disabled by default by the end of the decade. It's a real game changer. Finally, Section 5, How AI Escapes Python. Let's see why this entire execution model matters so much in the real world of machine learning. While alternative implementations absolutely exist, like PyPy with its tracing JIT for long-running loops, or MicroPython for embedded devices, CPython remains the absolute undisputed standard. Why is that? Because the machine learning ecosystem's answer has never been to just sit around and wait for pure Python to get fast enough. They've found a totally different way. Instead of trying to optimize the bytecode, tools like NumPy and PyTorch route completely around the Python virtual machine. When you add 2 massive arrays together in PyTorch, you're really only using Python to trigger a single bytecode instruction. That instruction instantly dispatches the entire heavy listing operation to a blazing fast ahead-of-time compiled C or CUDA kernel. So you pay the Python overhead tax exactly once per function call, not once per data element. This elegantly splits modern ML architecture right down the middle. Python acts purely as the control plane. It handles request scheduling, HTTP serving, and orchestration, which keeps development fast and agile. Meanwhile, C++ and CUDA act as the data plane, executing those massive mathematical kernels. The golden rule here is simple. Hot numeric loops bypass pure Python entirely. So as you walk away from this explainer with that 3-step pipeline diagram mapped out in your head, I want to leave you with a provocative question for your next project. When you're writing performance-critical code, are you wasting time trying to optimize Python bytecode, or are you smartly designing a system to route around it? Think about where your heavy compute actually lives. Thanks for exploring this with us, and keep architecting brilliant systems.